Oh. There are a lot of interference, so the lag is a bit annoying. Still 4 minutes. Oh. Change player. Oh, come on. It's like an orgy. Come on, move from there, guys. Posso iniziare?
Quando vuoi, sì.
Do you hear me? Yeah, okay. So, hi, I'm Roberto. I'm the lead developer of the uWSGI project, a contributor of various open source projects. The first thing I've learned as a speaker is never make demo when you make a talk. They never works. Are you agree? Okay, stop. Well, when you see demos like that one, you think most of the time there is something like Node.js behind or something like that, ugly technologies. By the way, in the last few years we have seen some kind of change in the HTTP world, in the web world. We are moving from polling way of asking for resources on the network to a real-time way. So we can make things like games, real-time communication like chat, video, and whatever you want. This talk is not about Socket.io. This is Socket.io is a workaround for having some kind of real-time communication, even for older browser. This talk is about Websockets. They are new technology. For new, I mean it is something that only recently has been standardized. The first RFC came out on February 2010, and until December 2011, there were 6 versions, all incompatible between them. RFC 6455 is the standardization of WebSockets. And it is currently supported on Firefox, Chrome, Safari, Opera, and I don't know, Explorer 10 says it supports them, but Bomber tab does not work. Well, the WebSockets protocol is composed by three parts. Handshaking, it is required for moving from a simple HTTP connection to a persistent connection with the server. Framing, so you don't need to worry about reassembling messages, and ping pong to maintain the connection alive. This is how the handshake at the HTTP level works. There's a normal old school upgrade connection in the HTTP. The only interesting part is the sec WebSocket key header. It contains a pretty randomic key. In the response, that key is hashed, and after that, the connection is established. You can start exchanging messages with the web server. Sorry, I'm not good on making slides. This should be a short representation of a WebSocket message. We can skip the first four items of the packet. The important one is opcode. It says if it is a ping pong packet, a message packet, or some kind of packet they will want to add in the standard in the future. There is a length of your message, a mask that is optional, and the effective payload of the message. Ping pong is opcode 9 and 10. It is required to maintain your connection alive. Moving from polling to real time introduces a lot of new security problems, especially from the resources point of view. You have a persistent connection, a socket connection always open with your web server, so you need so maintaining concurrency in such kind of setup is really hard and dangerous. So you need always to check if your peer is still connected, and connected in a good way. This is how you made a WebSocket connection from the JavaScript side, so from your browser. You instantiate a new WebSocket object using that kind of URL. You have on open event, on message whenever you get a message from the server, on error when you get error, on close when the connection is closed, and to send messages to the server, you use send. The server side in this talk is 100% Node.js free. All is proprietary. How many of you know the Blastbeard project? Okay, only my friends. Do you know Mongrel 2? Okay. Mongrel 2 basically works, is an HTTP server. It parses your HTTP request. It assembles them in ZeroMQ messages, and it passes them to one of the backend you have configured. It was written by Zed Shaw 3-4 years ago. Then he left the project, and when he left the project, I was sure the Mongrel 2 project would be dead in few months. So I started my attempt to make something similar aimed at games, because 20tab is my new startup that should be, one of its objectives is to make HTML5 games. So I started the Blastbeard project. It worked very similar to Mongrel 2. It used the routing engine of ZeroMQ instead of subscribe publish engine. It worked really well. It was really fun to develop on it. ZeroMQ is pretty easy as an API. But we started experiencing a lot of lag caused by the way ZeroMQ works. We suddenly realized that ZeroMQ is good for queue, not for real-time communication. The second error was trying to adapt the WebSocket standard to uWSGI. If you have some kind of expectation on the uWSGI standard, lose any hope. It is something I fear it never evolve again. It's some kind of religion. All the other standards like PSGI in the per word, Rack in Ruby evolved to support technologies like WebSocket. uWSGI, it's a dead end. So this was an error. The third error was trying to adapt the WebSocket standard to uWSGI. If you have some kind of expectation on the uWSGI standard, lose any hope. It is something I fear it never evolve again. It's some kind of religion. All the other standards like PSGI in the per word, Rack in Ruby evolved to support technologies like WebSocket. uWSGI, it's a dead end. So this was an error. Then we realized that WebSockets basically override HTTP. Once you establish a WebSocket connection, the HTTP parser, techniques, whatever you want, are completely dead. So let's override uWSGI too. We have uWSGI that is pretty versatile, or whatever kind of adjective you want to use. So we defined an API, a very low-level API. So one day, I suppose in 200 years, uWSGI will start supporting something like WebSockets. We can simply abstract this API. There are 3 main functions. One for handshaking the connection, so to exchange the headers we have seen in the previous slides. One call to receive packets from the client, and one to send them. There is a bonus one you can use with Gevent, async programming, whatever technique you want to use. That is the non-blocking version of the receive one. There is no ping-pong API, because it all is managed by the WebSocket receive function. In background, it continues pinging your clients and expecting pong from them. This is a simple echo application. Basically, you connect with JavaScript to the server. When you make the JavaScript object connection, the WebSocket handshake is called. You can pass it even the origin header. Do you know how origin HTTP authentication works? Okay. Pretty strange, but you can use this for authorizing sites to connect to external domains. Then it enters a loop. Those WebSocket receive, in background, it starts sending ping-pong packets, and whenever a message is received, it is sent back to the peer. Questions? It's okay? Well, when you want to make multiplayer games, concurrency is the main problem you have to fight. So you need fast communication between processes, threads, or whatever technique you want to use. I started making this prototype of uWSGI channels. There was a fast way to exchange messages between processes, threads, or a Greenlet, whatever you want. They were transparent for the developer. They were really fast, but they were really expensive. Each peer need to allocate 2 file descriptors, a chunk of memory for message exchanging. So I definitely removed them during development. So my current solution is using Redis publish-subscribe paradigm. Redis is probably the only software in the whole AT world that is perfect. You can say anything. You can throw all kind of shit to uWSGI, but you will never be able to throw shit at Redis. So, this is a multi-user chat. I don't know if you can look it. Okay. This is a non-blocking example. I've started soon with the heavy part. So, you make the handshake as soon as you connect. You connect to Redis soon after the handshake is done. You subscribe to the foobar channel. In that way, you can make a room for free. So you can have 1 queue for each room of your chat. Then you get the file descriptor of both the WebSocket connection and the Redis FD connection. And this is the more important part. You start waiting for both. This is the uWSGI async API. It's pretty low level. When you move to things like Gevent or Eventlet, it is a lot less code. So whenever the WebSocket file descriptor is ready, it receives a message in a non-blocking way, and publish it to the foobar queue. Whenever Redis is ready, it gets the message from the queue and send back to the WebSocket. It's some like broadcast messaging for all of your peers. So, multi-process, supposing you want to have a game like Bomber Tab, when there were 20 connected peers, you have to allocate 20 processes. It's not a good approach. You can use threads. They are good enough. It's a good approach for a lot of things. But coroutines for this kind of game are a better approach. Moving to Gevent, in uWSGI is pretty easy. You only need to add the options. And instead of using processes or threads, you start using Greenlets for each connected peers. Please stop enabling Gevent whenever server use GUnicorn, the Gevent WSGI server. Use Gevent with conscious. Cioè is the Italian word for? Okay, that is. Use consciously because if you have a part not Gevent friendly, your app is blocked forever. When you start developing game, the worst part of all the development phase is you have to take in account all the slow part of the whole software. If some part slow down, your play will go berserk and you lose customers and whatever you want. So try to optimize as soon as possible. I know it's a bad practice, but for gaming it is a requirement. So we started testing which combination was the best one. So instead of using the Gevent approach, so if you have Redis and WebSockets, you generate a Greenlet for each one. We use a Greenlet for each player. So a single Greenlet manages both Redis and WebSocket. And you need to reduce the Redis usage to the minimum because the IPC, the networking part of Redis, is the thing that very probably will slow down your app. For the best experience of your players, the synchronization part and the part managing the competition should be managed by the server. This avoids cheaters changing their code to spot a hole in your program. So in the Bomber tab example, everything is managed by the server, from collision to bomb explosion, whatever you want. The JavaScript part is only a really simple front end. We can say it as really a monitor that draws whatever the server tells him to draw. We have already used the demo. We will back to this soon. PyPy, I think, is the best challenge for gaming. As performance for gaming is really important. It's not like classic web development. Sadly, Gevent for PyPy is somewhat on development, doesn't work really well. There are a couple of attempts. The uWSGI asynchronous API we have seen before works really well with PyPy continuelets. Maybe I will release soon another demo of WebSockets using this approach. So let's start seeing some code. Scusa? It's good? Okay. I will show you how Gevent paradigm is powerful. The code is not really good, but should be pretty clear. Whenever you drop a bomb, a Greenlet is generated. And once you generate the bomb, here, Gevent sleep for 3 seconds. This is the time where the bomb waits for detonation. You have to don't worry about locking, race conditions. You simply generate your Greenlet. You tell him sleep for 3 seconds, and then explodes. This kind of approach to game programming, especially when you have a lot of concurrent users, is really easy, powerful. This is why I suggest you to try the Gevent approach in game programming instead of threads. We have a pretty simple class for the bomb. We have a class for the player. We have function for collision, pretty simple functions. Function for moving. Okay. Okay. And this is the main app that basically receives the commands from the client and calls the required function. One of the things I loved when switching from Blastbit to uWSGI, it was I didn't need to think about pure disconnecting, pure blasting the server. All is already battle tested in uWSGI. So I need only to define a function to destroy the player object when it disconnects. So 380 lines of pretty object code. Move this to Node.js approach. Someone loves callback-based programming? Oh, okay. No, stop loving it. So, back to slides. Okay. Well, a lot of standards are coming out for improving the web experience. The one I suggest you to look is WebGL. There are already engines for abstracting the OpenGL part in 3D programming. WebRTC is a good technology, but not for this kind of game. Use it for real-time audio and video, or especially for audio if you want your player to chat each one. And I need to complete uWSGI channels because Redis is perfect, but it's slowing down my game. Wait, another demo. I hope the web connection will work. I would like to show you how WebRTC is powerful, but okay. Sorry. This somewhat work only on Chrome. Okay. Oh my God. Okay, can you try joining this URL on the public network? Put your dresses on, please. It will not work, I'm sure. Oh. Okay, stop. Too much demo. The interesting thing about the WebRTC is only the shaking part, only the connection establishment part is managed by the server. After that, using various techniques like stun turn protocol, you make a peer-to-peer connection. What we have seen some seconds ago was a real connection between my browser and your browser. Okay, thank you for playing. Questions?
Hello, thank you for your talk. My question is about, you said coroutines, you speak about coroutines. Did you try Tornado IO loop instead of Greenlets?
No, because I'm not really good at that kind of programming. Now I'm used to coroutine or green threads, so, but I suppose it's a viable approach, yeah, for sure.
In terms of concurrent socket open, did you stress test the uWSGI approach? How many socket connection can you keep open?
Yeah, 1,000 really.
1,000. Okay, cool. Thank you.
The only limit is memory. The more memory you have, the more user you can manage. Because CPU usage is really, really low.
So you don't hit the number of socket open?
Oh yeah, you have to tune them. Yeah. No more questions? Okay.
Are you going to take it?
Yeah. Hello, how are you? I was just wondering, did you time the latency for the pub sub part of the communications? So when one gamer is sending up his events, like I've moved up, down, left, right, so you've got the latency from the browser to the server, then it goes into your, over the WebSocket, and then there's the next part from into Redis and out to all the gamers he's connected it. I'm just wondering, how fast is that bit in the middle? Did you time that?
I'm a all-time video game player. When I started looking for how gaming works, I remember those funny for loop with a sleep inside to sync with the refresh. I never realized that those kind of sleep was a signal for your CPU is faster than you think. So the latency is really low. Thanks to the jQuery framework we use, the game query, we can synchronize the refresh of the monitor, and we monitorized if there was too much latency, but it was not the case.
Okay, and just
computers are really faster than, than you think.
Related question: is it suitable for games where the client is sending up his state at, say, 10 to 15 frames per second? Or is it just for operations like
how many frames
per
second? 20 frames per second. Bomber tab. 60 frames per second was Bomber tab with 20 players. So.
Okay.
We found, especially on Linux, the CPU usage of Chrome was really high. I suppose it's because the graphics card driver. But on a system with good graphics driver, it should work flawlessly.
Try using Tornado Web. This truly asynchronous browser.
The uWSGI async API is really near to the Tornado way, but as I already said, I'm used to that kind of programming. But yes, Tornado is probably the best way if you want to use that kind of programming. And obviously, that kind of programming is a lot cheaper than using Greenlet or coroutines. They don't need the stack allocation or something similar, or stack swapping. Do you want to play again?
But I shut down the...
It doesn't want to replay.
Thank you. definitely.